All right. Oh, there we go. There's sound. I admit. Okay. How's everyone doing? Doing good? I'm very tired. All right. Today we're going to be talking about limits again analytically. We're going to learn the last handful of methods that we're going to use to evaluate limits analytically before we move on to section 1.4 on Thursday. Okay, so today should get us through section 1.3. You'll be able to do all the problems that I assigned on the homework from section 1.3 in case anyone's looked at the homework yet. Okay, so announcements, reminder, you've got homework due on Monday, again at 11:59 p.m. You'll be able to do some of it. You should be able to do the first, at least third. I assigned more than half, I think, of the from section 1.3. So you should be able to do a lot of it by the end of today. And then the reason I put homework on there that you don't know how to do yet is so that you can look at it and come to class with an idea of what you should be looking for specifically. So do look at the homework, even if you don't know how to do homework from later sections. Look at those problems to, be able to pick out what I'm wanting you to learn in class. Okay. Any questions on these announcements? Cool. So last time we covered the formal definition of a limit, and we used it to prove that some simple limits exist. Essentially, last time I showed a bunch of limits that exist just by plugging in the number that we care about, right? That was kind of the theme of yesterday, was if you're able to plug in a number into the function and get something, and the function's not piecewise defined, then most of the time that's going to be the right answer. I'm not going to say every time, because there will be exceptions, but most of the time, if you can just plug in the value that x is approaching, more often than not, you'll be fine. Okay, so we use this table here of limits to evaluate some simple limits. Are there any questions on these limits here that I have listed in this table? Because these, along with the composition rule, these were how we got all of our limits last time. Any questions? They should all seem pretty natural, that the limit of a sum is the sum of the limits, the limit of a product is the product of limits, and so on and so on. Okay. All right, so like I said, that table and also this composition rule last time was what we used to evaluate all of our limits, and these rules give us methods to evaluate all algebraic limits. And by algebra, yeah.
Can you explain that composition rule again?
Yeah, definitely. So all this is saying, really all this is saying is that the limit as x approaches a, the limit as x approaches a of f of g of x, it's really just saying if you're able to plug it in, to plug in x equals a, plug in x equals a. Okay, so this is equal to f of the limit as x approaches a of g of x, as long as f satisfies, well, we're going to see later that that second condition I have, the limit as x approaches L of f of x equals f of L, that means f is what we call continuous. We're going to see on Thursday that definition. But really, yeah, all this is saying is that if f is nice enough, then just try plugging in the x value a. Okay. And again, if f is not defined in a weird way, if it's just a square root of a bunch of stuff, or I don't know, e to a bunch of stuff, those definitions you're going to be fine just plugging in x equals a. So that was the composition rule. It looks complicated, but it really just says try plugging in the number. So we saw also last time that factoring is important. That was one of the first methods that we saw that wasn't really just try plugging in the number. Because if we try just plugging in x equals -3 here, what happens? Yeah, I get a 0 in the bottom. I get a 0 in the top too. I get 2 times 9 minus 33 plus 15. If you crank out the numbers, that happens to be 0 because I wanted it to be 0. So that tells me that I need to do a little more work here to evaluate this limit. So obviously, maybe not obviously, but the limit as x approaches -3, well, this guy, I'm bringing my work down here. The bottom, what is the bottom factor as? Well, we'll do the easy factorization first. Perfect. Anytime you have a squared minus b squared, and that's what we have here. We have x squared minus 3 squared. That factors as a plus b, a minus b. And that's actually going to be very important today when we talk about conjugates, okay? So, but this factors as x plus 3 times x minus 3, right? Does anyone know what the top factors as? Not quite, because we've got this 2 here, right? So I'm definitely gonna need a 2x, and then in order to get a 2x squared, I'm gonna need an x here. And so, yeah, it's 2x, 2x plus 5, and this is x plus 3, right? We definitely have to have a factor of x plus 3. Does everybody know why we have to have a factor of x plus 3? Okay. For anyone who doesn't know, who's afraid to say no, because when we plugged in -3 into the top and the bottom, we got 0. So anytime you plug in a number into a polynomial and you get 0, that means that polynomial has a factor of x minus whatever you plugged in. So we plugged in we plugged in -3, and we got 0. So that tells me that I have a factor of x plus 3 in this. Did it not write? Oh, sorry, I just didn't write 5. So we have a factor of x plus 3 in this polynomial. Any questions on how we got this factorization? Because once you know that x plus 3 is a factor, and the other factor has to look like 2x plus something, then it's not too hard to find that little extra bit. Okay, so the next step is what?
Cancel out our x plus 3s.
Yeah, I need to cancel x plus 3 before I can actually plug in -3, right? And the reason I'm allowed to cancel that thing that might be 0 in the top and bottom, again, is because we're looking at the limit. And that factor is only 0 when x is equal to -3, but that's exactly where I don't care exactly what's happening. I care about only what's happening close to that point. So you can cancel out that factor, and then when you do, I'm gonna learn everybody's names, but 2x plus 5 over x minus 3. Then we can plug in x equals -3 now, because it gives us no trouble now, right? So when I plug in -3, I get -6 plus 5 in the top. That scientists guess is a -1. And then when you plug in -3 in the bottom, -3 minus 3, scientists estimate that is -6. And so we just get 1 over 6. Okay. Do we have any questions on that? Thank you, Saba. Do we have any questions on this limit, how that factored, all that jazz? Okay, so again, remember, this is going to come up a lot today. A plus b times a minus b, this is how we factored the bottom. This is always a squared minus b squared. And a and b themselves can be any weird things, but anytime that you have two factors where I have one thing plus something else, and the other factor is that first thing minus the something else, when you multiply them, you get this nice looking polynomial. Well, it doesn't have to be a polynomial because a and b could be weird themselves, but you would still get this. Okay, so today we're going to talk about multiplying by the conjugate. It's a big method in evaluating limits. And we're also going to learn about the squeeze theorem. That's sometimes called the sandwich theorem if I'm hungry, and I'm very hungry today, so I might say sandwich theorem a few times. People do actually call it the sandwich theorem. Okay, and there's one other thing I forgot to mention, one method, but I put it in the notes. I just forgot to mention it here. But one final method is it's just simplifying fractions by getting a common denominator. Okay. So let's look at multiplying by the conjugate. I forgot to put the pauses in my Beamer slides, so I don't have the fancy reveal. But here we go. So last time I asked you guys to think about this limit here. How would you evaluate the limit as x approaches 3 of square root of 1 plus x minus 2 over x minus 3? This limit doesn't really play by any of the rules that we learned so far. Because first of all, if I just try plugging in x equals 3, I get 0 over 0, right? But then if I try to I can't factor the top, right? I don't know how to factor anything with a square root, okay? So the idea is it's kind of the opposite of factoring. Instead of pulling out something that I want to cancel, I'll put something else in that when I multiply, hopefully I'll end up with something that I can cancel, okay? And that's exactly what multiplying by the conjugate means. So when I say multiply by the conjugate, we're going to multiply by the conjugate of this, okay? And the conjugate, again, of anything that looks like a plus b. So here a is the square root of 1 plus x. B is 2. So we're going to multiply by the conjugate of that, or b could be negative 2 if you want. But the idea is that is a minus b. So if I multiply it by a plus b, then when I do that multiplication, I'll get a squared minus b squared, right? Just like in the previous slide. But then that square will get rid of the square root. Okay. So I say multiply by the conjugate. You're not allowed to just take an expression and multiply it by whatever you want. You're only allowed to multiply an expression by 1 and not change its value, right? So when I say multiply by the conjugate, I really mean multiply top and bottom by the conjugate, okay? So let's see what happens when we actually do this work. I'm going to multiply by the conjugate of square root of 1 plus x minus 2. And so that is square root of 1 plus x minus, or sorry, plus 2, minus 2 if you'd like. But again, I can't just multiply the top by that. I have to, if I multiply the top by that, and I don't want to change anything, I also have to multiply the bottom by that, okay? So I'm multiplying top and bottom by the square root of 1 plus x plus 2. Okay, so limit as x approaches 3. What does the top become? And this is the whole reason we do this. What does the top become? The top looks like a minus b times a plus b. So what do I get after I do that multiplication?
1 plus x
Yep,
minus 4.
perfect. Yeah, so I'll get, and to be super explicit about this, I'm going to get 1 plus the square root of 1 plus x squared minus 2 squared, right? But yeah, you're exactly right. The square root and the square cancel. And then in the bottom, I don't really get anything that looks very nice. But in the end, we are going to get something that looks pretty nice. Okay, so the top then, when you simplify, I'll actually come down a line, hold on. The top, when you simplify, becomes, so this is the limit as x approaches 3. This square root of 1 plus x squared, that's 1 plus x, and then minus 4 over x minus 3 times the square root of 1 plus x plus 2. Okay. And then what does that top simplify to?
X minus 3.
Perfect. X, the plus 1 and the minus 4 is going to give me minus 3. And now, what happens with that factor of x minus 3?
They cancel out.
Yeah, I get cancellation there and there. And so this is the limit as x approaches 3 of 1 over square root of 1 plus x plus 2. And now what do I do?
Don't you just rationalize?
Good question. If I rationalize, that'll actually get me exactly back to where I started. So in these problems, we're kind of like de-rationalizing with the goal of canceling a factor. Yeah, in other problems, if this was flipped, you would be, if we were looking at the limit as x approaches 3 of x minus 3 over square root of 1 plus x minus 2, then this technique, yes, would just be called rationalizing the denominator. And it would work the exact same way, but we sort of already did that work, and now we just plug in x equals 3, because when I plug in x equals 3, it doesn't, nothing bad happens, right? I just get the answer. So when I do that, I'll get 1 over square root of 1 plus 3. Well, that's the 1 over 2, and then I have plus another 2, so I get 1 over 2 plus 2 is 4. Okay. Any questions on that? So anytime you have something like this, where you plug in, you get 0 over 0, and you have square roots floating around, the first thing you should think is, I need to multiply top and bottom by the conjugate. And that'll usually be sufficient to get you to the answer. But in order to do that, you need to recognize what is the conjugate of any given thing. Okay, so we're going to have a quick little, not actual quiz, but we're just going to see, we're just going to write down what is the conjugate of 4 minus square root of x. And what is that conjugate? Conjugate of 4 minus square root of x. Well, this is A, this is B, and we have A minus B. So the conjugate then is A plus B, right? So what do I get for the conjugate then? 4 plus square root of x. Very good. And that's as easy as that. And again, finding that conjugate will help us when we're finding these limits. You can either think of it as rationalizing either the numerator or the denominator, but that's the whole technique here, is rationalizing one of those to try and get a factor to cancel. Okay. All right. So number 2, what's the conjugate of 3x plus the square root of 1 plus x squared? Perfect. 3x minus the square root of 1 plus x squared. right? Because this is just A, this is plus B, so we want A minus B. Okay, last one. What's the conjugate of conjugate of square root of 2x plus 1 minus 3? Yes, thank you. I'm very tired, guys. I'm sorry. So minus 3. Yeah, the conjugate is the square root of 2x plus 1 plus 3. Excellent. Excellent, excellent. Any questions on that? Okay, so let's use this idea to find the following limit. If it exists, the limit as x approaches 4 of 9 plus x, sorry, the square root of 9 plus x squared, all minus 5, and then divided by x minus 4. All right, well, what's the first thing that we should try? That's,
Multiply by the conjugate.
do what? Yeah, I
I
think,
was gonna say multiply by the conjugate.
yes, yeah, we're going to do that. The very, very first thing you should always try, and you guys probably just saw this already, is you should always try to plug in that number first and see what you get. And we get 0 over 0, and that tells us, yes, we're going to need to multiply by the conjugate. So when I do that, I'm going to multiply here, top and bottom, by what?
Square root of 9 plus x plus 5.
Square root of 9 plus, x squared
Plus 5.
plus 5. Excellent. Yeah, and so, and again, remember, you have to do this to both the top and bottom. Because again, it's just like rationalizing the denominator, only here we're rationalizing the numerator. Okay, so when I do that multiplication, this is equal to the limit as x approaches 4 of, what do we get in the top?
9 plus x squared.
Yes, perfect. We're going to get 9 plus x squared from that first part, because this is a minus b times a plus b. So this is a squared. And then what else?
X minus 4 multiplied by square root of 9 plus x squared plus 5.
That's true. We're missing something up top though. Yeah, because this was a squared, and so we also need minus b squared, 25. But then yes, you're exactly right. In the bottom, we're going to have x minus 4 times the conjugate of the top, or I guess the conjugate of the former top. Very good. All right, so now, so this was minus b squared. What does the top become? What's 9 minus 25?
16.
Yeah, minus 16, right? So we're going to have x squared minus 16 over, oh, that was a really bad division. There we go. Over x minus 4 times the square root of 9 plus x squared plus 5. Okay, and now what does that top factor as?
Plus 4 minus 4.
Yeah, we get another a squared minus b squared going on here. So this is the limit as x approaches, x approaches 4 of x plus 4 times x minus 4 over x minus 4 times the square root of 9 plus x squared plus 5. And now what happens? Yeah, we cancel that factor because math is on. So when we are done with that cancellation, we get the limit as x approaches 4. Well, now we had x minus 4, x plus 4. We cancel the x minus 4. So I'm left with x plus 4 over, and oops, just the conjugate. So the square root of 9 plus x squared plus 5. Okay. And then now what do we do? Exactly. We plug in our 4 because there's nothing bad is going to happen now. So when I plug in 4, I get 4 plus 4. Well, that is 8 over the square root of, what's the square root of 9 plus 16? Yeah, we get,
5.
yeah, thank you. We get the square root of 25 is 5, and so I'm going to get over 5 plus 5. So that tells me we get something that looks like 8 over 10. And if you want, you can reduce that. By the way, I genuinely don't care if you reduce your fractions in here. But you can, oops, you can reduce this by dividing top and bottom by 2, obviously, and get 4 over 5. But again, like, seriously, I don't care if you leave your answer as 8 over 10. Questions? Yeah, 0.8. Yeah, exactly. That's why I don't even really care if you reduce fractions, because if you put that into a decimal, well, guess what? Then that's 8/10 again. So. All right. Any questions on this one? Yeah.
I got a little lost in the beginning when we were multiplying the conjugate for the top.
Mm-hmm.
We became square root of 9 plus x squared squared
Mm-hmm.
minus 5 squared.
Yep.
What about the conjugate of square root of 9 plus x squared plus 5?
The conjugate of the square root of 9 plus x squared plus 5 is just the original guy. So we're starting with that. So we multiply top and bottom by the conjugate square root of 9 plus x squared plus 5.
Okay, I guess it's just confused with the minus 5 squared because of the plus 5 on the right for the second.
Yeah. Because this is the square root of 9 plus x squared. All of that is a, and then b is 5. And so again, when we do a plus b, a minus b, we're just left with a squared minus b squared. And so a squared is just 9 plus x squared, and minus b squared, well, that's just 5 squared. So that's where that comes from. Mm-hmm. Any other questions? Okay. So one other method before we talk about a more abstract one. One other method that you'll use in evaluating limits very frequently is just getting common denominator and simplifying. Okay, and that's related to the last couple examples too, because really you're just trying to simplify stuff with multiplying by the conjugate. So the only thing that I have found trips up students learning about this is like, how do you get a common denominator when you have 1 plus x in the denominator? If I want to add 2 over 1 plus x minus 1/2, I want to get a common denominator. Well, what is the common denominator here?
Two times 1 plus x for the numerator.
Perfect. So yeah, so this brings me to a point that in classes before this, when you're learning how to add and subtract fractions, your teachers probably told you need to find the least common denominator, which is wrong. You don't need to find you just need a common denominator to add and subtract fractions. Okay, and so if you're trying to add 1/2 and 1/4, yeah, the least common denominator is 4. But if you don't see that right away, you can always just multiply the denominators together to get, content. You can always multiply the denominators together to get a common denominator. So when I do that, this guy, I'm going to multiply by 2 over 2 so that the denominators will each have a factor of 2. And this guy, I multiply by 1 plus x, oops, 1 plus x over 1 plus x. And then when I do that, I'm guaranteed that they have a common denominator and I can add them together. So this is going to be 4 over 2 times 1 plus x minus, well, 1 times 1 plus x, so minus 1 plus x over 2 times 1 plus x. I'm going to put this in parentheses to be safe, because that minus really distributes. Okay. So when we're looking at this limit up here, well, we just simplified that top part, right? Because, well, I mean, there's one more step to do, I guess. The 4 minus 1 plus x, that's equal to 4 minus 1 is 3, and then distribute the negative to get 3 minus x. So the top becomes 3, this is the limit as x approaches 3, of 3 minus x over 2 times 1 plus x. And then all of that is over, because that was just simplifying the top, all of that is over x minus 3. Did I lose anybody there?
What's the denominator in the top?
The denominator in the top is 2 times 1 plus x. This work right here was to find what the top simplifies to. So this is, yeah, 2 times 1 plus x. Yeah.
Why didn't you distribute like the 2 on the denominator?
Excellent question. You can. In other problems, it's going, a lot of times you'll get some cancel, you'll be able to cancel something. So it depends on the context of the problem. I typically leave things, because I've done a million of these problems, I know with these problems where you're getting a common denominator and adding and subtracting stuff, usually you don't want to distribute that denominator because something might cancel and you're gonna distribute and then maybe have to factor out again. And so why take that extra step? That's an excellent question though. Yeah, sometimes it will be fine to just distribute, but most of the time you'll want to leave it factored in case you have any cancellation. Cool. All right, so we'll move on. Who remembers how to divide fractions? Because this is really, well, let me give myself some more room. This is really the limit as x approaches 3 of what? 3 minus x over 2 times 1 plus x. 3 minus x over 2 times 1 plus x. And all of that divided by x minus 3. X minus 3. And x minus 3 is really x minus 3 over 1, right? In case, I feel like that always helped me when I was dividing fractions. So what do I do with this fraction then? How do you multiply or divide? How do you divide fractions?
You multiply the numerator by the reciprocal of the denominator.
Perfect. Exactly. We flip this and it becomes a multiplication problem instead. Does everybody remember that? Flip the bottom and multiply instead of just doing division. So maybe I'll try my hand at art. We flip that. Oh, boom, beautiful. So this becomes the limit as x approaches 3 of 3 minus x. The numerator, the big numerator, the fraction in the numerator doesn't change. But then now we're multiplying by 1 over x minus 3. Okay. All right, and who sees what happens here? Yeah, exactly. This is really 3 minus x. I can rewrite that as negative x minus 3, right? And then when I do that, it's very clear that those cancel, right? The negative doesn't cancel. I still have a negative up top. But when I cancel those, I get negative 1 over 2 times 1 plus x. And now what can we do?
Add in the 3.
Yeah, we made it. We can just plug it in now. This is just negative 1 over 2 times 1 plus 3. And that's negative 1 over 2 times 4, so negative 1 over 8. Yep. Any questions? So those problems are a little long, I feel like, but as long as you can remember, like, you don't need the least common denominator, you just need a common denominator. Once that clicked in my brain when I was learning this, that made all these go so much smoother for me. So you just need a common denominator, so just multiply the denominators to be able to add these things when you have a problem that looks like this. Okay. And then make sure, another common problem that I see in calc students when they're evaluating limits is they don't simplify at every step that they can. And by simplify, I mean like canceling out things that you should be canceling out. And that will have you running into trouble, especially later. There's one rule. If anyone's taken Calc 1, you might know the rule I'm talking about. There's one rule that people like to apply, and then just plug in your number, and then, but if you don't simplify after using this rule, you could just get in this infinite loop of trying to evaluate the limit and then not simplifying, and then you keep doing this. So always simplify the function you're looking at as much as you can at each step. Questions on this? Excellent question. Someone asked, is this algebraic or analytic? I typically say these are analytic methods, but you can also, I mean, we're using algebra to evaluate this. So if you want to say algebraic, that's also fine. I'll make it very clear on exams and stuff what I want you. Essentially, we have 3 ways to evaluate limits: graphically with a table, and then you can say algebraically. That's fine. Yeah, call it algebraic if you want, or analytic. Yeah, I'll use those terms interchangeably. But they both, in this context, mean the same thing. Okay, so that brings us to our next theorem, and it's really our last theorem that we're going to learn as far as evaluating limits. And it's called the sandwich theorem or the squeeze theorem. And so the whole point, before I work out this example and show you the formal proof, here's the whole point. I've got this green function and this purple function. This guy is y equals x squared, the green one. The purple function is y equals negative x squared. And then I've got this blue function that's bouncing around in between them. And the blue function is pretty weird, and it's going to be hard to work with. But if I'm looking at the limit as x approaches 0 of the blue function, what has to happen looking at this graph? Well, the blue function is squeezed or sandwiched between the 2 bigger functions, right? And the two big functions, as they approach 0, as x approaches 0 there, y approaches 0 for both of those. And so because this function is squeezed between those, it has to have the same limit. This is the whole idea behind the squeeze theorem, is that if I can squeeze a function that I don't know a lot about, but if I can squeeze it between two functions that I do know about, and those two functions have the same limit as x approaches some value, then that function that I squeezed between the other two functions, that function has to have the same limit. That's the whole idea behind the squeeze theorem. Okay, so the very standard way that we use this is with the limit as x approaches 0 of x times sine of x. Well, the whole idea is, what do we know about sine of x? Sine of x is always between two numbers, and those two numbers are perfect, -1 and +1. Because if you think about what sine is, sine of an angle, you just draw the triangle and you scream SOHCAHTOA. And so sine is opposite over hypotenuse. And the opposite side is never going to be longer than the hypotenuse. So sine of theta is always between plus and minus 1. Okay? So here's where the magic happens. I multiply this whole string of inequalities here by x, and I get negative x is less than or equal to x times the sine of x is less than or equal to x. This is a true statement, at least for x positive. And so what happens to this as x goes to 0? As x goes to 0, what happens to x? It seems silly to even ask that question, right? What happens to x as x goes to 0? It goes to 0, right? As x goes to 0, x goes to 0. It's really silly. And then what happens to negative x as x goes to 0? That also goes to 0, right? Through negative values. Yeah, very good. And so what has to happen to this as x goes to 0? That has to go to 0. It's squeezed between these two functions that are both going to 0 as x goes to 0. So this has to go to 0 as x goes to 0. Okay? That is the whole essence of the squeeze theorem. We typically use it with sines and cosines, where we know we can bound sine and cosine by plus and minus 1. And so if I have something like here, this is x squared times sine of, I think it was x squared times sine of 1 over x. And so the sine of 1 over x part is actually oscillating faster and faster and faster as you get closer to 0. This is oscillating faster and faster and faster and faster and faster. And so typically we wouldn't really know how to handle that, but the x squared factor is squeezing that down to 0 as x goes to 0, even though we have this wildly oscillating thing. Okay? So that's how we use the squeeze theorem in practice. Here's the statement of the squeeze theorem. Remember the graphs that I just showed you. I think the graph that I showed you is much more enlightening than this definition and this statement of the squeeze theorem. Okay, so if you remember anything, I mean, if you want to memorize all this, you can. I would remember this graph, because this really captures the idea of the squeeze theorem. And it doesn't just have to be as x goes to 0, by the way. All the examples I give are x goes to 0. This could have been shifted around and it would still be true. Okay. Questions on the squeeze theorem? I'll say we're not going to use the squeeze theorem a ton. If it comes up on an exam, going to make it one of the hard getcha problems. Gotcha. It should be a kind of a free question. All right, so I think I have enough time to walk through this. Find, using the squeeze theorem, the limit as x approaches 0 of sine of x over x. And for anyone who forgets, this is what this sine of x looks like. It's this oscillating thing. That's a sine wave. And that's what it looks like, okay? So in case I don't get through all of this, the answer, and we get this by using the squeeze theorem, is 1. Okay? So, but let's get to work on trying to prove this. So the whole idea is actually, the proof of this is very geometric. Okay? So if that scares anybody, just remember that the limit as x approaches 0 of sine of x over x is 1, and ignore what I'm about to say. But here's the proof. So if we have, if this hypotenuse is 1 here, then, and if this is, I'm going to call it theta, theta is taking the place of x, then this here is sine of theta, and the bottom leg is cosine of theta. And again, you can just say SOHCAHTOA, you know, so sine is opposite over hypotenuse, hypotenuse is 1, so opposite has to be sine of theta. Okay? But I could also draw this similar triangle where this whole bottom length is 1. And if that whole bottom length is 1, then this length here is tangent of theta. I'll let you guys prove that for yourselves. But when you do that, the whole idea is we're comparing the areas of everything. So what's the area of the small triangle? What's the area, first of all, of just any triangle? One half base times height. So, oh, and I don't, sorry, the triangle I actually want is, I'm going to draw it in red. What is the area of this triangle here? Well, the base has a length of 1, and the height is sine theta. So the area there is sine of theta times 1 divided by 2. Okay, and what's the area of the big triangle? Of the whole guy? Well, that is tangent of theta. That's the height, and the base is 1. So tangent of theta times 1 divided by 2, right? And then here's the part that I think might upset some people. We have 2 areas, and then I'm also going to look at one more area, and that's the area of the angular sector here made like that. And the area of that guy is just theta divided by 2. How do we get that? Well, the area of a full circle of radius 1 is pi, right? Well, this sector of a circle is an angle of theta, so it's taking up 2 pi over theta, or sorry, it is theta over 2 pi of a full circle, right? Because there's 2 pi radians in a circle. And so you just divide the area, pi, by the theta over 2 pi that this sector is actually taking up, and you get the area of that sector has to be theta over 2. And so hopefully it's clear that the area of the red triangle is smaller than the area of the green circular sector, and that's got to be smaller than or equal to the area of the big triangle. Okay. Then the whole idea is if we flip everything, flip it all, we'll get 2 over sine of theta is now, if you flip everything, you also have to flip the inequalities, okay? This is less than or equal to, or greater than or equal to, rather, sorry, 2 over theta, and then that's greater than or equal to 2 over tangent of theta. And then I'll multiply everything by sine of theta. Okay, so when I do that, I'm going to get, oops, let me take one more step. When I do that, on the left, I had 2 over sine of theta. So when I multiply by sine of theta, I'm going to get 2. That's greater than or equal to 2 sine theta over, or sorry, that should be sine theta over theta. No, that's right. And then lastly, this is greater than or equal to 2 times sine of theta over tangent of theta. 2 sine theta over tangent of theta. Well, what is sine of theta over tangent of theta? Well, that's sine of theta over sine of theta over cosine of theta. So again, I flip the bottom and multiply because this is sine of theta over 1. I get sine of theta times cosine of theta divided by sine of theta. Okay, and so this on the right there is really just, all of this is just 2 cosine theta. So I get 2 is less than or equal to 2 times sine of theta over theta is greater than or equal to cosine of 2 times cosine of theta. And then you cancel all the 2's. And so we get 1 is greater than or equal to sine of theta over theta is greater than or equal to cosine of theta. And then hopefully it's clear that as theta goes to 0, 1 just stays at 1 the whole time, right? So this is going to 1 as theta goes to 0. Cosine of theta as theta goes to 0. Cosine of theta is a smooth continuous function. I know I haven't defined continuous, but I'm just trying to say you can plug in theta equals 0 into the right-hand side here. So when you plug in 0 into cosine of theta, cosine of 0 is 1, okay? And so that means that this guy that we're trying to show, this has to go to 1 by the squeeze theorem. If that was way too complicated, you're not going to need to know that proof. I do really want you to know that this is true, because that's going to come up later when we're talking about a very specific type of limit. This is going to come up later in the class. So I do want you to know this. If that proof was too much for you, forget it. I just wanted to show you that it is true, but this is the real thing I want you to remember here, okay? All right, do you have any questions? Okay, if not, please wipe down your desk as you leave. If you do have questions, I'm gonna be in my office after 1:45 today, so you can always stop in at like 2 if you'd like. Thanks, everybody.
Thank you.